Okay, so today, two completely different topics. I'm going to talk about something that I've done a lot of, so I know a lot about it, so I can talk about it uh, easily. And then that's this so-called idea of phase-encoded mapping. And the reason I'm going to go over this, it's not just because I did it, it's also an example of application of the Fourier transform, which we now know a lot about, application of the Fourier transform to data analysis. So, and then I'll talk about convolution in preparation for talking about the general linear model of how you analyze MRI data. So for that, we need to have the concept of convolution. And we already mentioned convolution before. I'll just go over it again, because we mentioned it with the convolution theorem, but I'll give an example with an actual hemodynamic response function. So starting off with the phase-encoded mapping. So the idea of a lot of MRI experiments is that you do something like you do condition A, and then you have some kind of off, and then you do condition B, and then maybe condition B again, and then off, and then back to condition A, and you try to figure out the response to a couple different conditions. But there's a lot of cases where when you're interested in investigating a map of some kind, where you really need a whole bunch of different conditions. Like you can sort of imagine that you need conditions for all the different locations in the visual field. And if you're going to try to make a map of the visual field, you could have hundreds of conditions. And so this method of phase-encoded mapping was designed to sort of deal with a situation like that where you're looking at a map. And the simplest example would be in the visual case. So imagine this is where the person is fixating. So the idea is here we're trying to actually find a visual map. So find how different parts of the visual field are represented in the cortex. And so we can sort of break this down into two different problems. So imagine we have a region of the cortex that represents that part of the visual field. So you can call this, the receptive field. So imagine you have a part of the cortex, a particular part of the cortex. So say you did a recording and you recorded from that part of the cortex. And let's say that there was a little map there. And so you're in that part of the map, and in this part of the map, the cortex responds to that part of the world. So that would be, up and slightly to the left. So now if you take a stimulus, and the stimulus I've often used is say like a little checkerboard, something like this, and it's flashing at sort of an epileptogenic frequency, because we know that that's the one that excites the cortex the most. So it turns out if you turn this on and off, about 8 times a second, like the transition between on and off, 8 transitions per second. If you turn that on and off like that, so like where when one square used to be light, you suddenly change it to black, that will give you a nice big visual response. So now if you actually move this, so if we move this guy slowly, for example, wrote every, say 64 seconds. So very slowly move it around. Then what will happen if you then look at the signal that you get out of the brain? What you would expect is that you would get a signal that would be something like the following. So here's time 0, and say we rotated it around 8 times. So what's going to happen, there'll be not much response at the beginning because we haven't got there, and then when it gets over there, you get a response, and then it rotates around again, and maybe there's another response, and then maybe the person wasn't paying any attention, or his eyes went somewhere else. And then, he was back paying attention again, and then he skipped a couple, and then back paying attention again. So you get something like that. So you would get, like, say, 1, 2, 3, 4, 5, 6, 7, 8 little responses. Now, what if the receptive field instead of being over here, so here's this guy, we'll put that guy in red. So this guy corresponds to this one. But what if the receptive field was, say, a little, down here? Say it was down, I'll make a green one. So the receptive field was over here. Then what's going to happen is there'll be a little bit more of a delay before it gets there. And so then in that one you'd see a response like this that was a little bit delayed relative to the other one. Something, like that. This is kind of more or less what the actual signal is going to look like. It'll kind of look like a mess. So this guy is this one. So it's a little delayed. It skips some every once in a while. So what is this? So this is something we know about. It's a time signal that has a periodic signal in it. So this is time going this way. And so we can do a Fourier transform of it. So if we do a Fourier transform of it, then what should happen? So how do we do a Fourier transform? Well, here's the real part. Here's the imaginary part. That's all 0. And so we do the Fourier transform of it, and what do we get? So we get all the different frequencies that it contains. So now we're in the frequency domain. So here's our frequency domain picture, and we will get a real and imaginary part, and they'll be like all different frequencies. So just our Fourier, our one-dimensional K-space. And then in order to view it, we'll turn that real and imaginary into a phase angle and an amplitude. So there's the phase angle and the amplitude. And then what should we see? So if we were in an area that had a big visual response, what we would expect to see is, when we look at the amplitude, we would expect to see maybe some movement artifact down here in low frequencies, but at the frequency of 8, we ought to see a spike, because there's a lot of frequency 8 in there. And then there'd be other frequencies, heartbeat, a whole bunch of other things going up to high frequencies. So if we saw something like that, then we would know that we found an area that was periodically modulated by our stimulus at the stimulus frequency, because we were rotating every 64 seconds. So for example, 8 cycles in, say, 512 seconds. So that's where the 8 comes from. So there will be 8 peaks. But so if we just look at whether or not there's a spike there, we can say, this area has a map of some kind, or it doesn't have a map of some kind. Because if there's no spike there, then it doesn't care. No matter what you're doing, it doesn't care. But then we have a second number. That's the critical thing. So our second number, so remember, this is frequency. So we'll have a second number, and that second number will be, from pi, from 180 to minus pi. This will be all the phases. And what the phases will correspond to, these are supposed to all be the same length. What the phases will correspond to is where you are. So if I go down, that's 8. If I go down and look at 8, I get a particular phase angle. And that phase angle will tell me where the receptive field is. So if the phase angle is advanced, then the receptive field is, maybe in the lower quadrant. And so this is a way of getting a second number, out of our one-dimensional signal. So we just have this one-dimensional signal. We just record. This is just the brightness. Yes, remember what this is. This is just brightness. Brightness of a voxel. Yeah, so that's just the brightness of a single voxel. So this, you'd have to do this at every voxel. So this is just the brightness of a single voxel going up and down, and we say it has a lot of 8 in it. So how would we sort of phrase this in a more traditional way? What we would say is we want to calculate the signal to noise. This guy is a signal, but then what is the noise? So basically these are noise. You can sort of think of these frequencies as noise frequencies. So these are noise freaks. So all these higher frequencies. That could be like, fidgeting, all different kinds of little stuff that we don't care about. And then this guy is a signal frequency. And then now what about this down here? So this is a real signal probably, because if you say you move, so what's going to happen if I move in the middle of this? Like, so, the signal's coming out like this, and then suddenly I moved, and then, the signal is going to suddenly be in a different place. Why is that? Well, that's because if you move a little bit, just a tiny bit, it's going to say you have a voxel that's sitting right here. That voxel is going to start off seeing something like this, and then if you move, it's going to see something like this. That's going to be a big signal difference, like maybe 5 or 10 or 20%. So suddenly, like, I did it the wrong way. So say you move so that the voxel got brighter. That was my example. So suddenly the voxel will get a lot brighter. And it didn't actually get brighter. It's just because, a movement artifact. So that's a real signal. So this is a what we call a nuisance variable, because it's not noise. It's not sort of something that we think is just random noise. It's actually something that really did occur. And so we need to regress that out. And so if you were thinking of this in a standard way of doing it, you would say, well, let's just sort of fit a very smooth contour to this. If you fit a smooth contour to this, and then we could essentially subtract that smooth contour out of this. And that would be, you could call that regressing this out. How could we do it here? We could just say, don't pay attention to those. So my, signal to noise, or you could also think of it as a variance ratio, an F ratio. Signal to noise is basically just equal to, the sig, divided by, average of noise freak. So basically, if I just compare this guy to the average of all these guys, if that number is big, that means I've got a significant response to this. And then we could just throw these guys away, because those low frequencies are probably a real signal that is actually affecting us, but it's not one that it's a nuisance variable. It's not one that we care about. So that's how you could pretty much do the same kind of analysis that you normally do, that we're going to talk about next time, general linear model. This is all linear. So when I throw away those frequencies, that's literally just like subtracting out. It's just like linearly subtracting out our movement artifact. Same thing. But the advantage is we've got this second number. We've got the second number, and that second number tells us where we are in the map. Now, notice it only told us where we were in polar angle, but the problem is we've got this guy just tells us the angle of the receptive field. So it just tells us that angle or this angle. It doesn't tell us how far away it was from the center. And so for that, we would need to do a second thing. So the second thing would be, let's make a little ring. It's not a very good ring. Let's make a ring like that with the same thing. So maybe it has, it's like a ring checkerboard. And flash that ring checkerboard at an irritating frequency that Marty always likes. It gives like a really big visual cortex response. And then slowly expand the ring. So, if you slowly expand the ring, then the same thing will happen. If you've got a receptive field that's sort of sitting right about here, what will happen is, if we keep slowly expanding the ring, and then when we're done, don't come back in, just start right from the middle, from the center again. So, expand the ring like this, like expand it, and then go back to the center and expand it. So if you do that, you'll get a periodic signal again, and the phase of the signal will depend on where you are. And then the last cool thing, you could do them at the same time. So because we're all linear, why don't we just turn on this and then also turn on a ring? So if we do this, so the ring is expanding. So this guy's going around this way, and the ring is expanding. But the trick is, let's expand the ring like, say, 11 times, and we'll rotate this guy 8 times. So what would you get then? If you did the Fourier transform, then you would see there'd be some noise artifact, and then there'd be a spike at 8, and then there'd be another spike at 11. So you can do them at the same time. They could just add to each other. So this guy will go around 8 times total, and then this guy will expand 11 times. So there are different frequencies, and so you could actually do this. You could map both the distance of the receptive field from the center. So we need to know this distance, and we also need to know this distance, and that's separate from knowing the angle of that guy and the angle of this guy. So we need two-dimensional thing, but that's an example of how you could do that. And you can apply this. You could apply this to other modalities. So in the case of the auditory system, you could, instead of moving something around the visual field, you could just slowly change the frequency. So if I over time change the auditory frequency, so this is the stimulus frequency. So if I slowly change the stimulus frequency, now I'll probably have to do it on a logarithmic scale or exponential scale like that, because we know that the representation of frequencies in the cochlea or in the brain is approximately exponential like that. So what happens is, if you say take 100 hertz, look where that projects to. You'll find that will be in this part of the map. If you look at 200 hertz, it might go here, but to go the same distance in the map, you'd have to go up to 400 hertz, and then 800 hertz. So that's approximately what the auditory map looks like. It looks like an exponential map, or vice versa. If we take the logarithm of frequency, that gives us a linear map. So what you could do, the same thing, you could just go up, like that repeatedly, and pretty much, etc., do the same thing. So you could look for a map of frequency. Or in the case of, the hand, the hand is another two-dimensional two-dimensional surface. So what you could do is you could say, first let's stimulate sort of the fingertips, and then a little later on we'll stimulate here, and then a little later on here, and then a little later on here. You could do that to try to figure out, this axis of the map in the hand, and then on a separate occasion, come in and just stimulate. First stimulate, this finger, and then go to this finger, and then go to this finger, and then go to this finger. And so that then you could get the two dimensions of the map on the underside of the fingers. So it's a very general thing. It can also be used for more complicated things. So an example that Ray Song Wong, one of my students, and I worked out was have somebody actually pretend like they're eating something. So the idea is you're sitting here, you're looking at a screen, there's just a fixation, and then a piece of food comes on. So you have to have a piece of food. So like an apple, there's a healthy piece of food, there's an apple. So an apple comes on the screen, and then you're still fixating, and then what you do is you reach out with your hand as if you're going to eat that apple. So you reach out to you actually stick your hand out in the scanner toward the screen, and then you bring it back to your mouth. So here's your mouth right here, happy mouth. So you actually sort of bring that apple, the virtual apple, back to your mouth. So if you do that repeatedly, that's a periodic stimulus. It's a periodic stimulus the same way that this rotating thing is a periodic stimulus. So fixate, target comes on, you reach for it slowly, and then you bring it back to your mouth, and then you put your hand back to the beginning. And then another target comes on, you look at it, you reach for that, bring it back to your mouth, and then go back to the beginning. So you can apply this method to sort of more complicated cognitive paradigms as well. And then as long as you do something repeatedly with about the same timing, you can apply this method. And so then you could sort of break up your signal into signals related to the target coming on, signals related to the movement, signals related to touching your mouth, things like that. So it's not just for mapping. You could do all different kinds of, any kind of action that you can arrange to be done periodically. You can apply this kind of method. Okay, so that's, and you could even apply the two frequency part of it. So if you have like an action within an action, so one action is occurring at a different actual periodicity, different numbers of total actions per scan, then you could even look at more than one. So for instance, you might do something like you might be saccading a bunch. So if you saccade, and then you saccade here, and saccade here, and saccade here, and then there's some other larger task, you might be able to look at activity related to the saccade versus activity related to two different tasks. So, okay, so that was sort of quick and dirty phase-encoded mapping. And that's been, heavily, all different kinds of versions of this have been heavily used for mapping lower and higher level, visual areas and somatosensory areas, and you can use it for movement. You could move different parts of your body and look at what part of the brain is activated. So it's quite a general thing, and it's since we already went over the Fourier transform in so much detail, it's a sort of handy way of using the Fourier transform to analyze data, not just reconstruct an image. So now plan is to talk about the more standard way that people analyze data, which is using a general linear model. But one of the things that we need for the general linear model is convolution. So let's talk about convolution. So convolution. So we talked about it before, but it never hurts to go over these things about 16 times in a row. That's about how long it takes, between like 16 and 64 times for me to actually finally remember anything. So the definition of convolution is, so here's a function. As a function of x, we'll just start off with x like a Photoshop filter. It might be sort of the x direction in an image. And so that function, so that's the final function, but we're defining it as the convolution of two functions with each other, two different functions. So it's an operation that occurs, so convolution is an operation that occurs between functions. Sometimes it's just written out as a star, but that can be confused with multiplication. So if we write it out as a star with a circle, then we can sort of say, so sometimes this is written like, f star g as a function of x. So there's all, if you look in the literature, there's all different kinds of ways of representing this. But so sometimes it's written that way, a little confusing. This way seems a little easier to me. So there's two different functions. We're doing some operation between two different functions, and what the operation is it's a little bit like a Fourier transform. So we're summing across this other variable that's not x. So we're summing across a different variable the following thing. So we take the first function at point z. I've got a typo in my notes. I'll fix one small little typo at the bottom. I'll fix that. So we take that function at z, and then we multiply it by the other function at an offset. And so this is at point x minus z, summed across all z. Now this operation, so there's another confusing thing if you just look up convolution and just Google convolution. So this is commutative. Not even spelled right. Commutative. And so what that means is you can reverse these and it will give the same effect. So I could do like, g of z times f of x minus z, and that would be exactly the same. And so often we talk about, we label this as, we'll call, say, the first one like the hemodynamic response function, or sometimes the kernel. That might be like a blurring kernel in Photoshop, as an example. And then this thing, is the image or the experimental design. So this is like the experimental design, or our image. So this is, the kernel or our filter. So that's one way of thinking about it, but because it's commutative, it doesn't matter. You could do it the other way around. So I could call this guy I could call G the kernel, and I could call F the image. So that's kind of, when you first run into this, it's like, whoa, I thought that one was supposed to be the kernel. Yeah, but it's commutative, so it'll go either way. So let's just draw it out this way. So like I did before. So basically the plan is we've got some function, some random function here. So say this guy is G. So this is our experimental design, or our image, and we're going to convolve it with this F, which is our sort of filter, or our hemodynamic response function. So so how do we do this? So here's our filter. So we have to do it for a particular x. So if we pick out an x, so this is x. So let's pick out this point. And so we're trying to calculate the convolution for that point. So we're trying to calculate the convolution for that point. So how do we do this? So let's just do this equation right here. So this equation says for one x, we have to sum across all z this thing. And so sum across all z this thing. So first we have our hemodynamic response function. So here's our f. That's our f. So there's the hemodynamic response function. And so how does it work? So first we go to z. So let's just pick out, say this point. So that's z. So we have to go across all z, but I'm just doing one z to start with. So we go to z, and then what do? We multiply it by the value of this function at x, which is right here, minus z. So that would be this point right here. So this is minus z. So we get this point, we get that point right there, and we multiply it by that, and then do it for all z. And so what does that look like? Well, that looks like, go here and get this guy, and go here and get this guy, go here and get this. Is sort of a complicated twisting mess. So why is it twisted? And then, this guy goes here. So why is it twisted? Another way of thinking about this, sort of just a conceptual simplification, is why don't we just flip the function? So if I flip this function like this, just reverse it like that, then my problem is easier. So then I can just go, multiply this guy times this one, and this guy times this one. That sort of makes it a little conceptually easier. That's the same thing. So we could either sort of go the opposite way in the function, or we could just negativize the function. That will work out to be the same. So what is the result? So the result is, when you do this flip method of thinking about it, you can sort of see it's like a cross correlation. You're kind of correlating this function with that one. You're sort of saying, like, how much does that one look like that one? Because when you multiply all those things and sum them up, that's a correlation. So basically we take that. So, and what have we gotten out of that? Here's our h. Our h is just one number. So that whole mess is just added into one number that belongs at point x. So we just got one number. So this whole thing, sum across this whole thing, and that just ends up at one number. So how do we calculate another number? Well, we just move over to another point and just do the same thing. And so we would have to move our f function, one over, do the same twist. But you might wonder, like, what's with the twist? Why do we have to twist? What's the reason for that? So when we think of it in terms of an actual convolution with a hemodynamic response function, it makes, we'll try to sort of give a intuition for why you want to do the twist. Why do you want to do the twist? So now let's change over from x over to time. So here's our hemodynamic response function. So that's our hemodynamic response function as a function of time. And so that would be, so this is our HDR. So that would be, if we did a very sudden stimulus, how would the blood oxygenation change over time? So we do a sudden stimulus right here. Here's the sudden stimulus on the 0. And then we record a whole bunch of data. We don't have to record before 0 because you don't need to find out what what the stimulus did before it occurred. So you just start at time 0 of the stimulus and then just record what the response of the brain is. And you could, the jargon for that would be an impulse response function. So we did an impulse, boom, just hit the brain with a flash. And now we look at what is the response after an impulse. So that's the hemodynamic response function. And then let's assume that our experimental design is, so let me get rid of this less vertical lines there. Okay, so say our experimental design is we turn a stimulus on, and then we wait a while and turn another stimulus on, and then we wait a less amount of time and turn a third one on. So here's our stimuli, A, B, C. So that's so this is the hemodynamic response function. So I'll write that out. Hemodynamic response function. And then here's our impulses, which is our experimental design. And so what the convolution is going to give us is what the actual brain response should be. But before we sort of try to explain why we want the flip, let's just sort of look at it in a more intuitive way. And so the more intuitive way of looking at this is, let's just assume we've got I'm just going to draw the exact same thing again. So here's the experimental design. I'll start with the experimental design because that's kind of the thing that's causing stuff. Okay, and remember it's commutative, so we sort of go back and forth. So we start with the experimental design, and then here's our hemodynamic response function. And so when we convolve those two, what do we want? So this is the intuitive way of thinking about it. Well, what we want is the brain response. So this is, X experiment, here's hemodynamic response function, and then we want response. And so what is that response going to look like? Well, at this point in time, you did a stimulus, and so what's going to happen is the hemodynamic response function will be released. And so you'll go up like that until you get to this point where there's a second stimulus. And so when the second stimulus happens, it's just going to add on top of it. So you'll have another hemodynamic response function added on top of that while this one is continuing to decay until you get up to this point in time. And then there'll be yet another one added on top of that. And then they'll all, and make that one go up enough. And then they'll all, start to die off eventually, something like that. So this is, this is the very intuitive picture of what's going on. We do some stimuli, they cause hemodynamic response functions, they add to each other. So why do we want to reverse? Well, let's just take an example. Here's why we want to reverse. So say we want to calculate the value of the convolution at this point in time. So this is all time. So we want to calculate the value of the hemodynamic response function at this point. So how do we do that? Well, what we do is we just take the hemodynamic response function and then reverse it like that, and then multiply it by this data. And so how do we multiply it by the data? If you look at what's going on, we have to, let me just draw it. Yeah, let's just draw it on top of there. So let me I'll put the stimuli back in. So here's the stimuli. So there's another one over here, and another one over here. Okay, so what does the convolution say? The convolution says just multiply all those pairs. So this is all 0 in between. And so when we multiply 0 times that, we don't get anything. So basically, the only terms that are going to add into our sum are these 3. So basically what we do is we just multiply, if our experimental design is 1, versus 0, so say this is 1 versus 0, all we have to do is just, find this part on the hemodynamic response function curve, add it to this part, add it to this part. So that's why you want to reverse. So how would we collect another time point? Well, here's another time point a little bit further into the future. And then all we do is we just put the hemodynamic response function over here, like that, and do the same thing again. So then basically you just get this point over here, and then add it to this point, and add it to this point. So that sort of makes more intuitive sense, So why is it that we reverse it? Well, the effect of this stimulus is kind of a long time after the stimulus occurred, and so that should be small. So that's why that guy is small. The effect of this stimulus, this third stimulus, it hasn't been very much time since that stimulus happened, and so that should be earlier on the curve. So there's a method to the madness. That's why you want to reverse. So it makes sense for it to reverse. And you could do the reverse just by subtracting, or you could flip the function, and then just not do the flip the function is equivalent of subtraction. So that's the convolution, and you can see it's related. It's somehow related to the Fourier transform because, for a single point, so for a single point in x, so here's the x there. So for a single point in x, how do you get that single point in x? You've got to basically sum across all z. So that's how. So it's kind of like, it's sort of the same kind of a thing as the Fourier transform, where each point in x depends on all of z. Z is running across the same variable as x is. So you could sort of think of it as, h of t, and then instead of using z, you could use t2. It's just another copy of the time variable. And so you have to sum across. So you basically have to sum across all time in order to get one point in time. So in that respect, it's kind of like the Fourier transform, where one point in k-space depends on all points in time. So every single point in k-space depends on all points in time. So it's a sort of a similar thing, and it's closely related because of the convolution theorem, sort of the multiplication versus convolving. But this just sort of writes it out again, and just in the context of time, to sort of really emphasize why we want this flip. So why is the flip? And so a little later point, where it's kind of the part that's conceptually difficult about the flip is that you always think of time as going to the right. It's like time is right. There's other cultures that have time as you're sort of going forward through time, but other people sort of think of it the other way. There's all different kinds of conventions in language for how people sort of view the timeline. But scientists, generally, time goes to the right. The plus x-axis is to the right. And so at first it sort of seems strange why you should do the flip, but it totally makes sense when you think about, for this point in time, this stimulus just occurred, and so that means that we should be sort of on the high part of we should pay attention to the high part of this hemodynamic response function, whereas for this point in time, that stimulus occurred a long time ago. So that means we should sort of be way out here on the fall-off part of the hemodynamic response function, and this is the way you do it. Just flip it over and multiply. Okay, we'll end the recording there, David.